Let's take a look at this differential equation, 4 minus x squared y double prime plus 2y equals 0. And let's find the series solutions of this differential equation. So starting off, 4 minus x squared y double prime plus 2y equals 0. So let's start off by writing y as a power series solution about 0. So x to the n, that's really x minus 0 to the n, but I'll suppress that. Okay, now we get y double prime is equal to summation n equals 0 to infinity of n times n minus 1 a sub n x to the n minus 2. Okay, now again, if n equals 0 or n equals 1, I can shift the sum. If n equals 0 or n equals 1, I can drop those terms. So I get summation n equals 2 to infinity of n times n minus 1 a sub n x to the n minus 2. And then I can shift so that I have x to the n here. That requires starting the sum at 0. So I have n plus 2, n plus 1, a sub n plus 2. Okay, now that would take care of the 4 term. I also have a more interesting case here. I've got an x squared y double prime term. So let's just take this and multiply it by x squared. I get summation n equals 0 to infinity of n times n minus 1 a sub n x to the n. Now this doesn't require any shifting. I've already got this set up with x to the n, so I don't have to do the same kind of gymnastics that I did here because I've already got x to the n here. So 4 minus x squared y double prime plus 2y, that's 4y double prime minus x squared y double prime plus 2y. So that's going to be summation n equals 0 to infinity of 4 n plus 2 n plus 1 a sub n plus 2 from this part. Then minus x squared y double prime is minus this, and I forgot x to the n here, minus n times n minus 1 a sub n x to the n. Then plus 2y is going to be this part, so plus 2a sub n x to the n. And that's supposed to be equal to 0. And all the sums started on term 0. They all got x to the n, so I didn't have to worry about popping off extra terms in front in order to be able to combine the series. Okay, so this becomes summation n equals 0 to infinity of 4 n plus 2 n plus 1 a sub n plus 2 minus n times n minus 1 a sub n plus 2a sub n, whole thing times x to the n equals 0. And so therefore the recurrence relationship is going to be that the thing in brackets is 0. So I have that 4 n plus 2 n plus 1 a sub n plus 2 minus, let's write it like this, n squared minus n a sub n plus 2a sub n equals 0. Now let's solve for the higher index here. A sub n plus 2 is equal to, bringing all this over here, I get n squared minus n minus 2 a sub n. And then dividing, I have 4 n plus 2 n plus 1. Okay, the thing in parentheses factors, that is equal to n minus 2 n plus 1 a sub n over 4 n plus 2 n plus 1. And so that leaves me with a sub n plus 2 is equal to n minus 2 over 4 times n plus 2 times a sub n, because the n plus 1's cancel. Okay, and so there is my recurrence relationship. Now it might be a bit easier to write this as a sub n as opposed to a sub n plus 2. So everywhere I see an n, I'm going to replace by n minus 2. So n minus 2 becomes n minus 4. Here I have 4. N minus 2 plus 2 becomes n. Then a sub n minus 2. And so there's my recurrence relationship where I conveniently drew through the 2 there, n minus 2. Okay, now this can be implemented with Excel. So if this is going to be column A, column B, row 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. So here are the values of n. So start at n equals 0 and then add 1 and fill down. So that becomes 1, 2, 3, 4, 5, 6, and so on. Okay, so a sub 0 is whatever it is. A sub 1 is whatever it is. And then this term is going to be equal to n minus 4. So a sub 3 minus 4 divided by 4 times n times the term that's 2 back, so b sub 1. So all that should be in cell B3. And if I fill that down, then that will be the way of numerically computing the coefficients of the first few terms in the power series.